بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Introduction to Reliability Engineering for Highly Reliable Component and System. This is video number 9, and in this video we will continue our series by us answering this question: what can be done as part of reliability engineering challenging to predict and to prevent each failure, how to manage failure, which is one of the main issues and the main requirement for applying reliability engineering. So far we discuss different alternatives, including the very early strategy, run to fail, and proceed to the time-based maintenance, predictive maintenance, and proactive maintenance. And under proactive maintenance, the main effort in proactive maintenance is to know why this failure, by running root cause failure analysis. Under root cause failure analysis, we have to do the investigation in a procedure approach, following certain steps and a certain process, and we can summarize this process into what we call it problem solving process. Under the solving of the problem, we have to know the difference between repairing the symptom or repairing the symptom and the cause. Of course, it is better if we able to very deeply dig out to know the cause of the problem. Otherwise, if we not eliminate the cause of the problem will reoccur again and again. So we have to know the difference between symptom and the cause. And to identify the difference, we will forward certain samples and certain examples of symptoms, and again some examples of the causes to know the difference between symptom and the cause. And as a problem solving process, we have to follow a certain approach, a certain step-by-step procedure, following 6 problem steps, and we apply these steps one by one to apply the root cause failure analysis. To know the root cause and to highlight the cause of any failure, we have to follow a procedure, step-by-step procedure, following certain problem solving steps. So we will discuss these steps. They are 6 steps to identify and to dig deeply to know the cause of the problem. And once we highlight the problem, once we know the problem, we then eliminate the root cause of the problem. Otherwise, the problem will reoccur again and again. To practice this approach, we will discuss many case history regarding very important failures and very critical failures. One of these failures is a very known accident which occurred in one of the Japanese nuclear power station. That was in August 9th, 2004, in a Mihama industry accident, and it is a very known accident, and we will able to discuss this accident and to learn from faults and from whatever occurs in the history. Another case study, which is a bearing case study, failure of one critical bearing, and how we can approach this failure step by step, and what actions we recommend to eliminate the reoccurrence of this bearing case. And so many cases actually we will also highlight in this video and in the next video as well. This is again one case history, a serious damage to the one of the very critical impeller pump, and what is the cause of this damage, and what is the different possibility, and how we can use the different symptoms, and how we can apply the 6 problem solving steps to identify the cause of this problem and to recommend the proper correction and the proper action. In the next video we'll have another case studies, including again one of the critical mechanical seal problem, and another motor problem. In the next video we will discuss more case studies. As I mentioned, under reliability engineering, we have to manage failures. What can be done to prevent and to manage failure and to prevent and predict failures? Starting from the early strategy, run to fail, time-based maintenance, predictive maintenance, proactive maintenance, and apply effective procedures to apply every one of these options. However, one of the important tools under proactive maintenance is to apply root cause failure analysis, which will be our subject in this video. What is the meaning of RCA, root cause analysis? It is a process of following procedures, and through these procedures there is a very established steps. One of the requirement is to collecting and analyzing data. It is not recommended to just make a guess and just come up with a proposal without knowing more details and collecting information and the data. And of course there are many sources from which we can collect this data, and we need to be expert on using this data and analyzing this data to come up with what is the cause of this failure and how to prevent it from reoccurring, not only in the present case, however, also to prevent it in the other cases or similar cases which might occur in different location or in different equipment. The expert of the analyst is to evaluate this data and to evaluate this information, and from this experience of analyzing come up with the cause of the problem. And doing that, we call this analyst and this group who handle this information and this data, we call them the slow team. This is in reverse to the quick team who is running the very quickly repair without knowing the cause of the problem. But here we should support the slow team who make a step-by-step procedures and following a certain approach to analyze this data and to come and lead him to discover the fault of the problem and to highlight and identify the root cause and the recommendation, the proper recommendation to eliminate this root cause from rehappening again and again. Otherwise, if we just repair the symptom, then the cause is still there. So we are not reliable, because since the cause is still there, it means our equipment is no more reliable as far as the main cause is still not corrected. So root cause failure analysis should be a step-by-step. We should not take a shortcut or make it as a very quick without considering and without analyzing all the information and all the data and collecting many data and many information to support this process. And through this video, We will apply these procedures step by step and realize how we can apply this approach. Another important definition to the problem-solving process, it is the process with the aim of identifying the root cause, not the symptom, but utilizing the symptom to trace and to guide us to the root cause of the problem or what events lead to that problem. And it is better and the best to solve this problem by correcting and eliminating the root cause rather than or opposite to merely addressing the obvious symptoms. Of course, symptoms is easy to realize. Root cause is not easy to realize. It needs effort, it needs time, it needs expert who do a process analysis and identify the cause of the problem. Our root cause analysis investigation actually is not limited to whenever we have a problem, whenever something goes wrong or goes badly or something fail. However, also we apply root cause analysis when something goes well or proceed efficient and properly operated. Why we apply root cause analysis for something which goes well, which is operating correctly and perform properly? This is actually to learn why it is operated properly, why it is performing well, why it is achieving the requirement as per the user require. This is to learn from. The analyst of root cause failure analysis all the time has to answer three main questions. What is the problem? Why did it happen? And what will be done to prevent from reoccurring again and again? So this is the main three issues, the main three questions the analyst of root cause analysis has to focus and has to answer. Of course, his answer is informed based on whatever data, whatever information, whatever analysis he been proceed, which enable him to answer this question precisely without any error in conclusion or error in recommendation. Why? Because any error in answering this question will, of course, reflect on the reliability of the equipment and it will create many consequences regarding the operability and the efficiency and the performance of the equipment. To answer these three questions, the analysis should follow a certain cycle. And the cycle will start by breaking down the big problem or multiple problem into small component. For example, if we have a very complicated system including multi mechanism or multi-stage or multi-discipline, including, for example, electronic component, mechanical component, fuel component, driving component, driven component, first stage, second stage, and so on. So we have to break down these multiple system into component. For example, we can start by analyzing the first stage, then the second stage. We analyze the electronical component, then we investigate the mechanical component. We investigate the input and then investigate the output. By this way, we facilitate the process and the analysis. Once we break the system into component, then we will able to check the system for input and output, and this will enable us to identify and specify exactly what is the cause, what is the problem, and we have to apply systematic approach. We have to follow the 6 steps and the systematic approach by using some tools and some aids like fishbone diagram, like fault tree analysis, like 5 why tools. This is Pareto analysis, prioritizing the fault tree analysis, and so on. So, by analyzing and using this systematic approach, we able to analyze the root cause and help us to identify exactly what is the cause of the problem, and then enable us to take the corrective action and the proper action to avoid the cause and prevent it from reoccurring again in the future. And this cycle actually is iterative cycle. Iterative means if we apply the corrective action and we test the action, then we get feedback, and based on this feedback, we might repeat this cycle again and again to make sure. So the problem is the cycle is not just to correct the action, however, also to test the action and to monitor the consequence of the action. And based on that monitoring, we take a feedback, and based on this feedback, we do an iterative process to view the performance and the correction, and to test for continuous improvement. To identify the difference between merely considering the symptoms compared with finding and eliminating the root cause, we ask 3 whys. Why high maintenance cost? Why equipment suffer low age? Why equipment suffer frequent failure? And the answer to these 3 whys is because we establish a poor maintenance program. Of course, poor maintenance program very much recommend and very much support quick team and appreciate the quick team as an opposite to the slow team. Quick team is the team who do a quick repair to the symptom, rather than the slow team who proceed step by step, apply approach, root cause failure analysis approach to highlight the cause of the problem. So if we're not applying the root cause failure analysis, actually it means we applying a poor established maintenance program, and we are very much support and appreciate the quick team who mostly act as a run to fail, as a reverse, as an oppose to the slow team who apply the root cause failure analysis. So we have to be very careful about the quick team, and not recommending the quick team very much compared with supporting the slow team who run the process of root cause failure analysis. Otherwise, our maintenance program will be classified as a poorly established program. Of course, the quick team will very much repair the symptom rather than repairing the symptom and cause. To know the difference between both team, between the slow team and the root cause analysis failure slow team, and the quick team who do the quick repair for symptom rather than identifying the cause. We have 2 different category of issues: symptom and cause. Any failure happens for reasons. These reasons, what we call it things, is just symptoms. These failures, what we see is a symptom. Symptoms, that is things which happen, which we realize, which we able to identify. However, behind these things, behind these symptoms, there is a reasons, and that those reasons, this is what we call the cause. Of course, not all causes required root cause analysis. We need time, we need effort, we need support, and of course, we should dedicate this effort and this time and this support to those causes which are very important and very critical. We have to understand the root cause, especially those important ones, those important cause for this important situation and those critical equipment, and we have then to provide the support and the time and the effort to control these causes and solve the failure of these causes, because it is one of the critical item, or if it is one of the very essential component. However, for non-critical component, we should not, we can tolerate, so it is again a matter of cost-wise decision. How much it costs us to tolerate these failures, how much it is if it is not tolerated, and how much it costs us to apply the root cause failure analysis, how much time, how much effort, how much money needs to support and to support the team for those very critical component and those critical failures. So we have to very much be familiar what is the difference between symptom and the cause. To highlight this difference, we will provide some example of symptoms and some examples of causes. And as we already mentioned, things happens for reasons, and these things which happen is a symptom. However, the reason is the cause, and we have to understand the important ones. And this is example of symptoms, whatever we can realize, whatever we can test, whatever we can feel, like vibration, temperature, pressure, oil debris and the contamination, leak, any crack or rupture or tear or wear or rust or corrosion, all this considered as a symptom. But behind this symptom, there are many causes. Could be for the symptom could be more than one cause or different causes. Again, as an example of causes, for example, if we have improper selection for certain material, or a material not compatible, or we have wrong specification. This specification is not as per our context, as not as per our environment or operating condition. Or if we do improper maintenance or improper surface or improper lubrication procedures, improper viscosity of lubrication and improper periodicity of lubrication, improper amount of lubrication, or improper type of lubrication, improper installation, we install it wrongly. We abuse the equipment or misuse the equipment, or we do some error in assembly, or even the manufacturing itself has certain defect or certain errors, or we do improper maintenance or some error in design is itself not match our requirement or our operating condition. During the manufacturing, maybe something wrong with the heat treatment during the fabrication of the spare part or the component or the equipment. So the list is very big. So this is just an example of the causes which might create symptoms. To identify what is behind the symptoms, what is the causes, it is recommended we proceed in a systematic approach, step-by-step procedure, starting and applying what we call 6 problem-solving steps. The first step is to identify the problem, identify the issue, identify the failure. This is done by what we call the problem statement. That enable us to very precisely understand what we are talking about, what we are discussing, which problem we are discussing. Because unfortunately, some meetings might not discussing a different issue at the same time, and every group or every person in the meeting might mean something different, or believe in something different, or consider some different issues. So we have from initially highlight and very much make it clear that we are discussing certain event or certain specific problem. And we should formulate what we call the problem statement. And the problem statement should include three parameters. Number one, what is the defect? And what is the failure, and what is the expectation. So we will consider these situations or these issues when we discuss case studies and apply this requirement for a problem statement. Number two, select the specialist people who are able to collect the information and analyze the information. The team should be properly formulated and leading by a facilitator or a team leader who can introduce the problem and who can manage the meeting to discuss the issue, and who able to control the meeting. And the team should be properly constructed as a number and as a specialist who understand the problem under investigation. Number three, the team will start to collect information and the data from different sources, from the machine itself, from the OEM manual, from the history of the equipment. They should go to the site and collect gauge reading or meter reading, and able also to meet people who are operating and who are maintaining the equipment and discuss questions and get answer. And from this they collect data and the evidence and the information which help them later on to identify and enable to know and analyze the data and come up with the problem and the cause of the failure, and also identify the root cause of the problem, and then implementing the proposal or whatever recommendation or whatever change, whatever modification to change the system and to upgrade the system, or to correct some error or some improper behavior, whatever, to eliminate the cause of the problem. And also they have to follow up the recommendation. Their recommendation has to be tested, and again to do a sort of iterative process to come up with another alternative or another modification or another recommendation, as we will see later in our case study we will mention here in that video and in the next video. Now we will consider two case history, and in the next video we'll continue with other cases. The first case history is this very famous accident which occurs in one of the Japanese nuclear power station in Mihama industrial accident in August 9th, 2004. And this is the layout of the system. It is a power station, nuclear power station, steam turbine, and this is the component of the system. And this is the location of the problem or the failure. This is the location of the broken pipe. It is a broken pipe here in that nuclear power station, And this is explosion in this pipeline. It was very huge, was very severe, as we see here. This is the explosion. This is the pipeline explosion, which is located here in that in that location. This is in the secondary circuit of the secondary vapor circuit. Fortunately, it was not radioactive circuit. Otherwise, the problem will be very high consequence. But fortunately, it is not in the radioactive system. It happens after the heat exchanger and before the steam boiler. And the rupture here, actually, that power station was established. That failure take place after 23 years from establishing this power station. And as per the recommendation and as per the policy of this type of stations, it has to be subjected to a fully inspection. Details, very special details inspection every 10 years. Of course, this is in beside to the normal procedures of daily maintenance, but every 10 years it has to be subjected to a very details and very restricted test and inspection for every component in the power station. It means that this is power station has been subjected at least to twice type of this detailed inspection. And why it was not actually identifying any problem in this power station. Actually, this pipeline was subjected to a very severe thinning. The pipeline is starting from almost 5 millimeter thick, and when the failure occurs, they measure the thickness. It was almost 1.5 millimeter. And when they do the investigation about this accident, they realize that during these 23 years, none of the detection or inspection technique reporting any thinning in that pipe. Although this thinning is starting from the early life, and it takes 23 years to come up to that very low thickness, because they actually do a wrong inspection. They not mentioned in the inspection the organization which run and which maintain this station does not inform it that this type of pipeline has to be inspected using ultrasonic inspection technique. They claim that we not inform it and we not being asked to do ultrasonic inspection because it is not mentioned in the maintenance procedures details and requirement. So we apply, they claim that they apply visual inspection to the exterior of the pipeline, and of course that external visual inspection will not tell the thinning which could happen inside the pipe. And the lesson we can get from this accident actually is to apply the proper procedure of inspection and to ask why even this thinning happening, why not pipeline is not compatible with the media inside the pipe to avoid that thinning. Of course, that thinning could happen because of corrosion or erosion or chemical action or whatever. So initially, why this pipeline was not reliable? It was not reliable because the material of the pipelines is not compatible with the media. That's why it's subjected to that wear and that thinning during that period. The second, the learning we learned from this accident is to all the time use the proper inspection technique to explore the hidden failure. Of course, this is type of a hidden failure. It's not obvious to the maintenance personnel, or it's not obvious to the operating personnel. It is a hidden failure. Unless we have the proper inspection and the testing technique, we could not explore the thinning procedure and take the action at the proper time. So this is one of the historical failure case study which we can learn from. An accident and failure case study is a very critical bearing which has a frequent failure, and the way of handling this failure. What approach we can consider to handle this failure? Actually, we have the early approach, which is simply replace this bearing whenever it fails. However, this is against the reliability, because this machine where this bearing was installed is no more reliable because we are running the firefighting or the run to fail by simply replacing this failed bearing. And we might support the fast team who are capable of doing that repair very quickly and very professionally. However, this is against reliability. We better to support the slow team who come up with why this bearing has a frequent failure. If we apply the root cause failure analysis, we do investigation, and the investigation of that failed bearing might indicate many reasons. One of the reasons, it might not be lubricated, or it might has the improper lubricant, or the improper viscosity, or the improper amount, or even there is a blockage in the passage of the oil lubrication, or poor lubrication system. Whatever the cause, we should come up with the cause of the problem, as an opposed to that firefighting team who just simply replaced the failed bearing. And in that case, they repaired the symptom. But under reliability, we apply root cause failure analysis. Yes, we will replace the symptom. We replace the bearing because the symptom is the failed bearing. But behind that failed bearing might be there is misalignment. There might be improper installation. Even the bearing itself is not the proper type, or the installation clearances is not properly controlled, or whatever the cause of the problem. In that case, we will eliminate the cause, and on the same time we repair the symptom. In the next video, we'll have another case study, which is a serious damage to one of the critical impeller in one of the single unit pump, which is essential to the operation process, and we will see why this severe damage to this impeller.